On the face of it, steering is the easiest system on the car to understand. You turn a steering wheel, the front wheels pivot, grip and roll in a new direction. The front of the car swings round and the rear follows on behind. It seems simple. So all we have to do is to take a look at the mechanical linkage between steering wheel and road wheels, and we've covered it. Well, not quite. To start with, the driver needs the steering to perform to certain standards. The steering wheel should be reasonably light to turn, so it's not too tiring. It must be precise, both on the straight and through bends. The road wheels should have a tendency to return to the straight ahead position of their own accord after a corner. The steering should prevent road shocks being transmitted to the steering wheel, though not so completely that the driver is isolated. He or she needs to feel, even subconsciously, how the front wheels are behaving. As well as all this, the steering geometry must allow for, but not be affected by, the tiny amount of natural give in the suspension. One of the simplest steering systems is a bicycle's. A single wheel connected directly to a pair of handlebars. And because there's relatively little weight bearing down on the steered wheel, it's easy for the rider to turn it. On a car or commercial vehicle, however, with roughly half its weight on the front wheels, some form of gearing has to be used. Without it, the driver would never turn the steering wheel. The most common design today on vehicles other than the heavier commercials is rack and pinion steering. The pinion, a cog at the bottom of the steering shaft, meshes with the rack, a toothed bar lying between the front wheels. Turning the steering wheel has the effect of moving the rack sideways. This in turn causes the road wheels to pivot and point in a new direction. It's a simple but highly effective system. The alternative to the rack and pinion system, mostly found on heavy goods vehicles, is the steering box. Various types have been used over the years, each containing a different form of gearing: the cam and peg, worm and nut, the recirculating ball. In each case, the box is located at the end of the steering column and is linked to the wheels. It translates the steering wheel's turn into so many degrees of turn of the front wheels. The gearing in the steering box normally means it will take 4 or 5 full turns of the steering wheel to pivot the front wheels fully from left to right. Any less and the steering would be too heavy to turn. On the other hand, on a car with rack and pinion steering, it will probably take as little as 2.5 turns from lock to lock.
The design and layout of rack and pinion steering is much the same on one model as on the next. There's a steering shaft that runs between the steering wheel and the rack. In the event of a frontal collision, the shaft will fold up at the universal joint in the middle so it doesn't push into the car. The shaft is enclosed in a steering column, which usually has a convoluted can arrangement that concertinas to help absorb any impact. The steering wheel itself attaches directly to the top end of the steering shaft. While there are many different designs, most are padded for safety reasons. There's a pivoting arm at each end of the steering rack. These are known as the track rods. The rack bolts to either the car's body or a body subframe so that it lies between the two front wheels. The track rods attach to an arm on the steering knuckle of each front wheel by means of ball joints. The bottom end of the steering shaft attaches directly to the pinion of the rack and pinion arrangement. As the steering wheel is turned, the pinion turns, and so winds the rack from side to side. This moves the front wheels to left or right via the track rods. As we've said, a simple and effective system, although that's where simplicity ends.
The first subtlety of steering design is seen on corners. When a car's travelling in a curve, each wheel is tracing an imaginary circle. All these circles will be of different sizes. But for every wheel to roll freely, the centres of all 4 circles must be in the same place, in this case the middle of the roundabout. Because the rear wheels always remain parallel to each other, the circles they trace are bound to have the same centres. Those at the front do too, but not because they stay parallel to each other. Indeed, if the circles traced by those front wheels are to share that same centre, the front wheels can't stay parallel to each other. On any corner, the inner wheel must angle more than the outer.
The geometry of actually achieving this depends on the position and length of the steering rack and track rods relative to the axle line. This axle line is a line drawn between the pivot points, called the swivel or steering pivots, of the 2 front wheels. On many cars, the rack and track rods lie behind this axle line and are also shorter. As we've seen, there's a ball joint on the end of each track rod. This connects to an arm on each steering knuckle. The arm is so angled that this ball joint lies to the rear and inside of the steering pivot. This means that each wheel is pulled by its track rod further than it's pushed. So on any corner, the inside wheel angles more than the outer, to just the right degree. The same result is in fact achieved on other cars in exactly the opposite way. Here, the rack and track rods are positioned in front of the axle line and are longer. This means that the arm on the steering knuckle must now point in a quite different direction, so that the ball joint is to the front and the outside of the steering pivot. The inside wheel on a corner is now pushed further than the outside wheel is pulled.
The front wheels of a front-wheel drive car will always try, in a sense, to pull ahead of the body. Of course, the suspension doesn't allow them to do so, but because the inner transaxle end of each drive shaft is more firmly anchored than the outer end, this attempt to pull ahead of the body translates into a slight turn inwards. To counteract this effect, the steered wheels are set so they point slightly outwards when the car is at rest. This is known as toe out. On a rear-wheel drive car, the forces exerted on the steered wheels are completely opposite. The driven wheels attempt to push the body ahead of the steered wheels. This has the effect of trying to turn those steered wheels outwards. In this case, the designer sets the front wheels so that they point just slightly inwards when the car is at rest, toe in. The terms tracking or wheel alignment are often used to refer to both toe in and toe out. Another factor the steering designer has to grapple with is the effect of the weight of the car bearing down on the steering pivots. On a bicycle, the rider's weight bears down on the centre of the handlebars, the steering pivot, which in itself is in line with where the front tyre meets the road. This creates very light steering, often referred to as centre point steering.
On the car, the steering pivot can't be in line with where the front wheel meets the ground. It can't be above the wheel. Instead, the pivot is to the inside of the wheel. And because of this, its vertical angle is critical. If the wheel and steering pivot were both truly vertical, a line drawn through the pivot would meet the road some distance inside the centre of the tyre contact area. The weight of the car would bear down along this line, so creating twisting forces between pivot and wheel. The result would be very heavy steering. For this reason, the steering pivot is set at an angle, and sometimes the wheel at a slightly opposite angle. The line drawn through the pivot, the force line, will now meet the road in the tyre contact area, so achieving a form of centre point steering. In fact, to retain some feel in the steering, the pivot line often meets the road towards the inside edge of the tyre contact patch, not the middle. As we saw in one of the programmes on suspensions, this angling of the wheel is called its camber angle. It can be positive or negative, and it may vary from positive to negative with the action of independent suspension.
From camber angle to caster angle. Any vehicle steering should have a tendency to run straight and naturally go back to that straight-ahead position after a turn.
The principle can be seen on casters fitted to furniture and to trolleys. Extend the line of the wheel's steering or swivel pivot. Then draw a vertical line through the centre of the wheel, and you'll find that the centre of the wheel is offset from the pivot line. The result is the wheel naturally trails behind this pivot line, whichever way the trolley goes. On the car, the angle of the steering pivot is adjusted to achieve the same effect. The line of the pivot meets the road slightly ahead of the vertical line through the centre of the wheel. The angle is small compared to trolley casters, but enough to make the wheel return to its straight-ahead position unaided.
Although not exclusively a feature of a car's steering, oversteer and understeer nonetheless have a bearing on how a car negotiates a bend. Whenever a car goes round a bend, because of the cornering forces, the wheels may slip sideways slightly over the road surface. The path a wheel takes is slightly different to the path along which it's pointing. The angle between these paths is called the slip angle. On gentle bends with a car driven fairly slowly, these slip angles are small. But the tighter the bend, or the faster the car travels, the greater these slip angles become. If the slip angles of the front tyres are greater than those of the rear, a car is said to understeer. It has a tendency to run wide on a bend. For the driver, this means he needs to turn the steering wheel further than might seem necessary for that bend. In general, it's true to say front-wheel drive cars have a natural tendency to understeer, although this is only really noticeable when powering through a corner. By contrast, rear-wheel drive cars have a natural tendency to oversteer, the slip angles of the rear wheels being greater than those of the front. But again, this is only really a factor when powering through a corner. In both cases, where too much power is fed to the driven wheels, it will reduce their tyres' grip, so encouraging understeer or oversteer. But whether a car understeers or oversteers, it must handle consistently in all circumstances. It mustn't, for example, display initial understeer that turns to uncontrollable oversteer for no apparent reason.
Come on, Steve, we're going. Come on.
An unusual feature that some manufacturers have experimented with is four-wheel steering. Although the rear wheels don't turn nearly as much as the front, it has certain advantages when manoeuvring in tight spaces. Out on the open road, the rear wheel steering progressively reduces to nothing as speed increases. What has become increasingly common on both commercial vehicles and cars is power steering. A power steering system not only reduces steering effort, it also helps to isolate the driver from road shocks that otherwise, on a large vehicle, might make the steering wheel twist disconcertingly. Early systems tended to go too far, taking away the driver's sense of feel for the road surface. Modern systems strike a balance, reducing road shocks but retaining an important degree of feel.
The various different types of power steering all use hydraulic power to assist the movement of the steering linkage. In the case of Transit, the power steering system is based on the rack and pinion design. It's positioned in the vehicle the same way, and the steering shaft turns a pinion that engages with the rack to turn the front wheels. Under the bonnet, there's a power steering fluid reservoir and an engine-driven pump. When the engine's running, fluid is pumped to a rotary valve between the pinion and the bottom end of the steering shaft. Pipes carry the fluid from this valve to either side of a hydraulic piston built into the rack. As the steering wheel is turned, the rotary valve releases pressurized fluid to one side of the piston. The pressure pushes against the piston and so assists the movement of the rack. The valve allows the unpressurized fluid on the other side to return to the fluid reservoir. As the steering is turned the other way, the rotary valve reverses the process and directs pressurized fluid to the other side of the piston. On progressive power steering systems, a special rotary valve is operated electronically. A sensor monitors the vehicle speed, and a module adjusts the passage of fluid through the valve. In this way, the driver is given most help at low speeds, when parking, for instance. As vehicle speed increases, power assistance is progressively decreased, giving the driver ideal steering feel whatever his speed. A second sensor monitors the changing angle of the steering wheel. This allows the module to recognize sudden steering movements at high speed when the driver starts to swerve and instantly reduce the assistance even more. There's very little routine service required on the modern steering system. If power steering is fitted, then the fluid level in the reservoir must be checked. If it needs topping up, the technician must check for leaks in the system. The tracking, toe in or toe out, may need adjusting from time to time if, for example, the driver has scrubbed a front wheel against a curb or when new tyres are fitted. If tracking is out, tyre wear may well become uneven. There is one more job that may have to be done, although it's by no means a routine service item. After extensive use over a number of years, it's possible that the ball joints on the end of the track rods may have to be replaced.
In the 12th unit of this series, we'll be looking at vehicles' braking equipment, discovering two main types of system. There are traditional drum brakes, often still used at the rear, and the more powerful disc brakes, almost universally used at the front. We'll see how the force on the brake pedal is amplified and transmitted hydraulically to the brakes, with the system usually split for safety. We'll see how braking effort is shared differently between front and rear wheels depending on the load and the vehicle's movement on its suspension. Then we'll see how the problem of wheel lock has been ingeniously solved by the electronic ABS system.